So this is going to be a set of videos on some of the hardware-based exploits that have been discovered that are based on some of the techniques we use to speed up computers. Somehow we are going to end up using those to break into computers. Spectre is the prototypical example of this, and we'll go through all of the details about exactly how it works. But first I want to give a little bit of a history of it because it was really quite a big deal when this was discovered. It was discovered in about 2018, somewhere in there. Although these kind of timing attacks that Spectre is based on had been known for a while, this was a new one, and it was one that seemed to affect almost every computer. We'll talk about the details of what a side channel timing attack is and all that stuff in a little bit. But basically, the important thing here is that it was discovered by the good guys. People were looking for vulnerabilities to be able to patch them. And they discovered this process whereby you can steal secret information from a memory space that you don't have access to, right? If I'm the attacker and you're the victim, you're keeping a secret in your memory space, I can steal it using this mechanism. And the solution that was proposed was to replace your hardware, right? All CPUs are affected by this, and so we should just get new CPUs. This was the initial response when this vulnerability was announced. Later on, I think it was the next day, the CERT gave a slightly changed bit of advice. But their initial advice when it was initially discovered was the underlying vulnerability is primarily caused by CPU architecture design choices. Fully removing the vulnerability requires replacing vulnerable CPU hardware. And that's true. You can't get a machine that is immune to this kind of attack. But you can fudge it, you can fix it. So the rephrased advice is operating system updates and application updates mitigate these attacks, but they don't actually remove all the possibility of these attacks. And this persists to this day. The particular architectural features that speed up machines that allow us to do things the way we do are also still, in some ways, can be vulnerable to this attack. And we'll see exactly how it works. So it affects all computers. And there is no hardware patch because it's a physical hardware that would have to be fixed. Software changes help a little bit, but don't do everything. And again, it attacks a core performance improvement. This is a key feature that we use on almost all machines that we'll talk about in some specifics. So the core mechanism for this attack is called speculative execution, or in other places in my channel, we talk about branch prediction and a bunch of other stuff like that. This is that. So the idea with speculative execution is you have to make a choice. As the CPU, you're trucking along executing instructions, and you have a choice to make. Either do this chain or this chain. Now, you could just wait until the choice resolves, and it takes a few cycles for that branch to resolve, that choice to resolve. So you can just wait till that resolves, or just start executing one of the branches. Because we use pipelining, execution of instructions are overlaid, many overlaid with each other. And so you just start executing one chain while you're waiting for the branch to resolve. If you guessed right and executing the right chain, great, you're carrying on. If you guessed wrong, you have to throw away the results and start again, but you're no further behind as if you had just waited. So it is almost always a good idea to just start executing one chain. But this is the feature that the attack can exploit. There's a bunch of other features that we'll talk about a little later on, out-of-order execution, branch prediction, caching, and stuff like that. But the key is to recognize that machines will execute instructions that they're not supposed to, or they probably wouldn't normally do, just in case they might need them later, and we can make use of that. And then the direct risk that is exposed by this is an idea of shared resources. When you have multiple processes executing on a machine, and most computers today have multiple resources, multiple processes executing at the same time, they each take a turn running on the CPU. So I'll run a few instructions and you run a few instructions. Or if we're doing hyperthreading or symmetric multitasking, we might do like interleaved. I'll do one and you do one and I do one and you do one. But the speed up features of the machine, things like branch prediction tables and cache, are sometimes shared between processes because they don't really matter, right? Whether I do a branch prediction globally or locally, There are global techniques and local techniques, but you can see the same improvement with a much simpler implementation if you just have a branch predictor machine that uses all of the code, that is accessible by any process. And so it's such a low-level thing that processes don't even know that it's happening, right? Process says execute this instruction, and then the machine, the actual processor, decides that it's going to try to guess which branch is going to run or not. You can send hints and stuff. There's a lot of details in this, but basically, every time there is a branch in your code, there will be a little tiny finite state machine that predicts whether it's going to be taken or not taken. And then those are updated as the processor proceeds through your code so that it has a better idea of the characteristics of each branch in your code and everybody else's code. But this is a shared process. Cache, in some cases, is a shared process. Virtual memory translations, a lot of stuff like that. All of this stuff can be shared processes that sort of fly in the face of the idea that I should have my resources and you should have your resources, right? Memory separation means like I shouldn't be able to see your memory and you shouldn't be able to see mine, and that works, right? The memory predictions and protection bits and stuff like that mean that I can't just read your memory, but I can trick the machine into giving me a little bit of information, making use of all of these techniques. The speculative execution aligned with the idea of shared resources. So the first variant that we're going to talk about, and I'll give you the full details in the next video, is a variant called variant 1. This is the core Spectre, is that it makes use of the fact that branch predictors learn which way to go as the code executes, and you can mess with that. And it also makes use of the fact that the cache memory stores recently used data closer to the CPU, right? There's videos about cache in my channel as well. But what cache does basically is if you're going to go to memory and read a word from memory, it's much, much, much slower than the CPU, many tens of thousands of times slower. And so if I'm going to have to go all the way there, I want to bring a bunch of stuff with me, so that if I have to access this piece of memory, probably I also have to access this piece of memory. So again, on spec, we'll just bring in a bunch of data and hope that we have the data that we need. This brings the data closer to the CPU so it can be faster. But again, there are aspects of that cache memory that are shared such that you can trick it. I can't actually read somebody else's cache. That would be a violation of the memory separation. But there's other tricks that we can do. So in the next video, I'll walk you through the details of the specific Spectre attack.